All right, so this is a repetition of what we did in class on Tuesday. For people that weren't in class on Tuesday, we're going to look at triple integrals. So conceptually, the idea of a triple integral is I have some lima bean shaped thing that exists in space. So let me draw my x-axis and my y-axis and my z-axis. So I have my x, y, and z axes here. And I have some voluminous solid, or some lima bean type solid, some bean that has some depth to it. Right, we have some solid that's three-dimensionally formed. And what we want to imagine is that inside of this thing, let's go inside of this thing. If I open up and get inside of my little solid, that this space contains some cubic elements, some little cubes. Again, paralleling everything we've done with single integrals and double integrals, that we have some little cubic element that in the center of it is some point P, which is its little element xk, yk, zk in the center of this cube. And then in the cube sides are, the delta in x, since it's parallel to the x side, the delta in z, because that's parallel to the z side, and the delta in y, because that's parallel to the y side. And so that we have some cubic entity inside of here. And we have k partitions of these, so this has some volume in v of k. So we have this little cube inside of our weird lima bean, and we expect to have k n cubes stacked inside of here. And so our job, of course, always is to find the sum of our k elements from 1 to n. Again, we can have some function applied over each point, some density function, some heat function, and whatever the change in volume is. And our game's always going to be the same. We're going to see a sum, we're going to do that sum over a change, and the sums turn to integrals. And in our case, the change in volume is equivalent to the change in the x element, the change in the y-th element, and the change in the z element. And so we either want to take the size of the partitions to 0, right? Take the volume elements down to 0, or we want to take the number of the elements up to infinity. Both will have the same effect. As we take the size of the partitions down to 0, the number of elements we'll need to fill the volume goes up to infinity. And so if we have some function integrable over this this region, this solid region. So your book calls this a solid region D. and f is integrable over d. And that line, over d, not over d. And so this Lima bean shape, this function can be integrable over it. And so as we take the limit, our sums always turn into integrals. And so we'll have some sum over d, or some integral over d, becomes the function in x, y, and z of dv, the volume element. Now, of course, we'll look at different coordinate transforms for different volume elements. But for right now, the way we set up our partitions particularly, we can integrate across dx, dy, dz. And so our job then to find integrations is to find this function that's integrable over a bounded region in space and integrate across all three axes or coordinates that we use. If I just wanted to find the volume element itself, or what the volume was itself, then in this function becomes 1. And so the volume of a volume contained within a bounded solid region D is the integral across that region, dv. And what we want to do when we find these integrals is, one, we sketch the solid region. With its shadow on one of the planes. And for example, we're going to look at this shadow projected onto a plane. For example purposes, we're going to use the XY plane. Then what we'll do is we'll extend an array, extend array, M, parallel to Z, the Z axis, noting when it enters the bounded region, D, and when it leaves the bounded region, D. Three, we'll extend an array. I'm going to try to keep the same nomenclature as the book. I think L is what they use. Yeah. Extend an array L. Extend array L parallel to the y-axis. Noting when it enters the shadowed region R, and when it leaves R. And then finally, 4, we note the minimum and maximum x values that bound the region R. And so there's a dimensionality scaling down here. We start, with our three-dimensional object, and we pierce through it with our kebab stick, so to speak. And then I'm going to make a smaller grid here. There we go. And so let me get my X and Y axis here. So we'll make a shape here. And get a Z axis going through. All right. So here's my X axis. Here's my Y axis. Here's my Z axis. And so we're going to have some shape. Some bounded region. So with some curvature to it. And we're going to project the shadow. So if we shine a light down, there's a shadow of this in the XY plane. Let me get my line straight down. It's coming straight down to here, there, coming straight down to here, here. And so we have some shadowing of whatever happens here. So this is R, and this represents region D. And so we'll follow our steps here. We'll start at some point beneath our solid region, and we'll project upwards through our plane. And so this is M. And we're going to note how it pierces the bottom and how it pierces the top. And so this is when it enters D, we're going to note what Z is. And when it leaves region D, we're going to note what Z is. And then we're also going to look at some ray L. And we're going to note what Y is when it enters R. What is Y? And when it leaves R, what is Y? And then in we look at the points. Well, that's definitely not parallel. That kind of bound region R, and we look at what x equals here, some x equals a, and some x equals b. And this lets us build our integral, because what we're going to get in our triple integral out of this is we get some relationships onto how these functions enter. So we started by piercing this bottom. So that part of the integral gives us z equals some function of x and y, right, some value here, and then it leaves where z equals some other function of x and y, whatever's determining the bottom cap and the upper cap. Then when we look at these limits, we're going to look at y equals some function g of x coming in, and y equals some g2 of x coming out. And then finally, we look between a and b. And whatever function is integrable over the region D times our element. In this case, we're going to do dz first, dy first, and then dx first. So this process doesn't have to be in the order of going parallel to z first. You can choose any axes, but your first axes that you're parallel to, then your function will be in terms of the other two variables. And then when you come down here, the next axes that you're parallel to, your function will be in terms of the remaining variable, and then you bring it back down into limits itself. So we'll look at an example where we'll look at a spherical region on the next video.